So in this video lecture, we will discuss about the threaded binary trees and the binary search tree. So first we will discuss the threaded binary tree. So what are threads? So in a leaf node or also in internal node, okay, in the leaf node, both the left and right subtrees are null, and but in the internal node, the left or the right subtrees may be null. Okay, if the internal node has both the left and right child, no left or right children is null, right? So, so threads are basically used when there are null left or right pointers. Okay, so for example, say a node which does not have a right child will have a null right pointer. Okay, so on average, you can see that say if there are n nodes in the binary tree, so on average, half of the nodes, that is n by 2, can have null pointers, right? So it means that half of the space will get unused because you are just storing the null pointers or just storing some sentinel value pointing to the header nodes, right? So what we can do, we can store some other useful information instead of storing just the null values, right? So if there are some null pointers, that is if the left subtree or the right subtree for some nodes are empty, then instead of storing just the null pointers in those nodes at the left and right position, we can store some extra useful information. Okay, so those kind of pointers, those kinds of values, and those values are themselves pointers. Okay, so those pointers, those extra pointers are called threads, right? So null left and right pointers may be used for storing some useful information. These pointers are called threads. That is, the extra pointers we are storing are called threads, and such binary trees are called threaded binary trees. That is, those binary trees which have threads in them are called threaded binary trees. Okay, since threads are pointers. Okay, so but these are different from the normal pointers. Okay, normal pointers in the binary tree means the left pointer and the right pointer. Okay, so for example, here the node B, its left pointer points to its left child, node D, and the right pointer points to its right child, node E, right? So these are regular pointers in the binary tree. Okay, threads are special pointers, so it must be distinguished from those regular or normal pointers, left and right pointers. Okay, so in the figure, we use dotted lines to denote the threads. Okay, so here this is a thread pointer, another thread pointer from node F to E, from node E to A. This is the thread shown with a dotted line. Okay, and the normal regular pointers are shown with the regular lines, okay, solid lines. Okay, and in memory, that is the representation in the memory, these are distinguished from the normal pointers by using a single bit. Okay, that is, with each pointer you can store a single bit. If the value of that bit is say 0, it means that the pointer is a normal pointer. Okay, and if the value of that bit is 1, it means that the pointer is a thread, a special pointer, right? So you can use single bit with each pointer to denote to identify if that pointer is a normal pointer or a special thread pointer, right? Okay, so we can have different types of threaded binary trees. Okay, so we have in order threads, we have in order threaded binary tree, we also have pre order threaded binaries, but we don't have post order threaded binary. Okay, so we have threaded binary trees for in order and for pre-order, right? And the in order threaded binary tree can be of two type also, one-way threading and two-way threading. Okay, that is the first one uses the one-way threading, so it's called the right in threaded binary tree, and the other which uses some different kind of threading, it's called the left in threaded binary tree. I will be discussing them in the next slide. Okay, so in order threads. So in order threads, right, so we what is in order. In order is also called left node right, because the root node is traversed before the right subtree and after the left subtree, L and R, right? So in order or L and R. Okay. So what happened in the in order threads when you use the in order threads? So if there is an empty right pointer in a node, okay, for example, see this node D. Okay, node D is a leaf node, so both the left subtree and the right subtree of node D is empty. Okay, left pointer points to null, right pointer also points to null. Okay, so here you can see that the right pointer, this dotted line basically shows the right pointer of node D, so it points to the node B. Okay, and you can notice that node B is the node B comes after node D in the in order traversal of this binary tree. That is, the node B is the in order successor of the node D, right? So if you write the in order traversal of this binary tree, so in the in order traversal, you traverse the left subtree first, then the node, and then the right subtree. So let's write the in order traversal for this binary tree. So okay, this is the root node. You will traverse the left subtree first. B is the root node of this left subtree. Then traverse the left subtree D, then the root node B. Okay, then the right subtree of node B, F, then E. Okay, then A, the root node, then right subtree of root node A. Okay, this part. So C is the root node. So left subtree G will be traversed, then root C, then the right subtree of node C. Okay, so it will be L, J, L, J, then root H, and then its right subtree, which contains just a single node K. Okay, so this is the in order traversal of this binary tree. Okay, you can see that P is the in order successor of node D. That is, node B comes just after node D in the in order traversal of binary tree, of this binary tree, right? So node B is the in order successor of node D. Okay, so you can see that this thread, the dotted line, is from node D to node B because node B is the in order successor of node D. Similarly, F has a thread to node E because node E is the in order successor of node F. Here, node E comes just after node F, so node E is the in order successor of node F. So this thread from node F points to node E. Okay, the right pointer of node F is also a null pointer. Okay, so you can store some useful information over there. So you store a pointer which points to the in order successor of this node F, which is node F. So this pointer will point to E. Okay, node E also has an empty right subtree. Okay, so its right pointer is null. So you can also store a pointer which points to the in order successor of node E. Okay, and the in order successor of node E is A, right? So node E, the thread at node E points to node A in order successor. Okay, likewise for any node, in any node which does not has a right subtree, which has a null right pointer, you can store a thread which points to that node's in order successor. Okay, at node G. Okay, in order successor for node G is C. So you can store a thread in order thread which points to C. Okay, at Lj, so thread at the L points to J. Okay, at J we also don't have a right subtree. Okay, so JH, H is the in order successor. So this thread points to H, right? Okay, so in this figure you can see that at a node which don't have a right subtree, we have stored a thread, a special pointer which is called the thread, okay, which points to the in order successor. And this kind of the thread is called in order thread. Okay, so an in order thread points to the in order successor, right? And since this in order thread, this kind of in order thread which points to the in order successor is stored in the right pointer field of the node. So these kind of binary tree are called right in threaded binary tree. Okay. So in the right in threaded binary tree, we store the in order threads in the right field of a node, and that right thread points to the in order successor of that node. Okay. And right pointer of the last node point to null because or it may also point to the higher node if it exists. Okay. So here node K also does not have a right subtree, so its right pointer is also null. But since this is the last node, there is no in order successor, so it simply points to null, or it may points to the header node if it exists. Okay, right. So this is uh, one-way threading. Okay, and in this one-way threading, we are storing a thread in the right field of the node, in the right pointer field of the node, and that right pointer or right thread points to the in order successor of the node. Okay, another kind of one-way threading is that when we store a thread in the left field, left pointer field of the node, and that left thread points to the in order predecessor of the node, right? So, and that kind of binary tree which uses these kind of threads stored in the left field are called left in threaded binary tree. Left in threaded because the thread have been stored in the left pointer field of the node, and those left threads points to the in order predecessor of the node. Okay, so these kind of threaded binary trees are called left in threaded binary trees. Okay. In another kind of binary tree, we can store both the left, we can store the threads in both the left and the right pointer fields of the nodes if they are equal to null. Okay, and those kind of binary trees are called in-threaded binary trees without left or right because we are using both the left and right pointers, so we call them in-threaded binary trees. Okay. So in the in-threaded binary trees, we store both the left threads and the right threads. Okay, left thread points to the in order predecessor, and the right thread points to the in order successor. Okay, so this example is an example of in-threaded binary tree because here we use both the left and right threads. So here you can see that at at node F we don't have any children. Okay, both the left and the right pointer are empty, so its left thread points to the in order predecessor, and the right thread points to the in order successor. Okay, so you can see here F. Okay, node F, its in order predecessor is node B and successor is node E. So left thread of node F points to the node B and right thread points to the node E, right? So all these nodes, so you can see here there are left and right empty, left and right empty subtrees. You can store special thread pointers. The left pointer, that is the left thread points to the in order predecessor, and the right points to the in order successor. Okay, the left pointer of the first node and the right pointer of the last node points to null, because obviously there is no predecessor of the first node and no successor of the last node. Okay, for example, node D is the first node in the in order traversal, so there is no predecessor node for the node D, so its left pointer will still point to null in the threaded binary tree. Okay, and K is the last node, so there is no successor of node K, so its right pointer is still points to null in the in threaded binary tree, right? So we have the in order threads. Okay, we have, in summary, we have two kinds of in order threaded binary tree. Okay, one is called the left in threaded, other is called the right in threaded. And if you are using both the left in threaded and the right in threaded, then we just call the binary tree as in threaded binary tree. Okay, so if you are using only left or right threaded binary tree, then this is called an example of one-way threading. Okay, and if you are using both the left and right threading, this is an example of two-way threading. Okay, so what are the use of these threads? Okay, what are the uses of these threads? Okay, obviously, if you have threads, then you can traverse the binary tree in the in order, either in the forward direction or in the backward direction very easily. Okay, if you are using the right integrated, if you are using the right integrated binary tree, then traversal in the forward direction in order is very easy. Okay, and using the left integrated binary tree, you can traverse the binary tree in order in the backward direction also very easily. Okay, if you don't use threads, then you must use stack. Either you will be using a recursive program, and you know that the recursive programs are easy to write, but their execution time is more than the non-recursive versions. Okay, but in the problem with the non-recursive versions, that they are not easy to write. You must use explicit stacks. Okay, so I have given this program, this assignment, this program, that is the non-recursive version of the in-order, pre-order, and the post-order traversal of the binary tree in assignment, and you will see that while writing the program, you must store all the node values. Okay, so that you might backtrack if required, and backtracking is required when you reach a node which does not have a right subtree. Okay, so in that case you must backtrack and go to the previous node. Okay, so in those scenarios you require the in order successor or the in order predecessor if you are traversing in the backward direction, right? So if you have already stored the in order threads either left or right, okay, then writing the algorithm becomes very easy for the in order traversal. So that is the use of the in order threads. Okay, so in fact you may avoid the use of the stack if your binary tree is an in threaded binary tree. Okay, and if there are no in order threads, then you must explicitly use the stack for keeping for keeping the exact order of the traversals of the nodes. Okay. Pre-order threads, likewise, the in-order threads, we can define the pre-order threads. Okay. So if there are no left or right subtrees, you can store some extra threads in the pre-order threaded binary tree, right? You can define the left pre-threaded binary tree and the right pre-threaded binary tree. The left pre-threaded binary tree, in the left pre-threaded binary tree, the left pointer of the node points to the pre-order predecessor. Okay, and the same way in the right pre-threaded binary tree, the right pointer will point to the pre-order successor. Okay, so pre-order threads can be defined in the same way. Okay, there are no post-order threads. Now we will discuss another type of binary tree, which is called the binary search tree. Okay, and obviously the use of this kind of tree is for searching. Okay, that's why it's called binary search tree or BST in short. So a binary search tree is a kind of binary tree that is either empty or in which every node contains a key that satisfies the following condition. All keys in the left subtree of the root are smaller than the key in the root. Okay. And all the keys in the right subtree of the root are greater than the key in the root node. And the left and right subtrees of the root are again binary search trees. Okay, so this is again a recursive definition. Okay, the first 2 points state that the all the values in the left subtree must be smaller than the key stored in the root node. Okay, and the second point says that all the keys in the right subtree of the root node are greater than the key stored in the root node. Okay, and the left and right subtrees are themselves binary search trees. Okay, so each left and right subtree of each node must follow these two properties, first and second. Okay, that is all the values stored in the left subtree of any node must be smaller than the value stored at that node, and all the values stored in the right subtree of that node must be greater than the value stored at that node. Okay, if these two properties are true for all the nodes in the binary tree, that binary tree is called the binary search tree. Okay, for example, see this node, this binary tree. Okay, this is a binary tree because the degree of each node of this tree is either 0 or 1 or 2. Okay, you have at most 2 children of any node. This is the binary tree. Now check if this binary tree is the binary search tree or not. Okay, so the condition for the binary search is that the value in the left subtree must be smaller than the value stored in that node, and the value stored in the right subtree of that node must be greater than the value stored at that node. Okay, so check for all the nodes. Okay, start from the root. So 50, we have 50 at the root node. Now check its left subtree. Are the values stored in the left subtrees are smaller than 50 or not? So you have 25, 30, 40, 35. All values are smaller than 50. Okay, so this is true. Then check the right subtree of the root node, 60, 70, 65. All these three values are greater than 50. Okay, so these two conditions are true for the root node. Okay, so now check these two conditions for other nodes of this tree, of this binary tree. Okay, now check for this node, 30, 25 left subtree is smaller than 30. Okay, 40 is in the right subtree which is greater than 30. Okay, fine. 35 is in the right subtree of 30. So it is also greater than 35. Okay. So the both condition are also true for this node. Okay. 25 is the leaf. Okay. So these two conditions are also true for this node. Now check for the 40. Left subtree you have 35 less than 40. There is no right subtree. So these two conditions are also true for this node 40. Now 35 is the leaf nodes, again condition true. 60. Okay. Left subtree is empty. In the right subtree we have two values 70 and 65, both are greater than 60. So again fine, no issue. Now check for 70. Okay, left subtree contains 65 which is smaller than 70. Okay, fine. Right subtree is empty. So these two conditions are also true for 70. Now check for this last node 65. Left and right subtrees are empty. So these two conditions are also true for 65. Now we have checked all the nodes of this binary tree and these two conditions are true for all these nodes. Okay, so this binary tree is a binary search tree. Okay, that is for any node we have checked that all the values in the left subtree of that node are smaller than the values stored at that node, and all the values in the right subtrees of that node are greater than the values stored at that node. Okay, so this is a binary search tree. Now check this binary tree. First check if this is a binary tree. Yes, this is a binary tree because the maximum degree is 2. Now check for the binary search tree. Okay, now check if all the values are correctly positioned. Okay, we have 8. So you must have all values less than 8 in the left subtree 13647, right? And in the right subtree all the values must be greater than 8, 10, 14, 13. Okay, so root node is fine. Now check, you can check for other nodes. Okay, so overall this tree looks fine. Okay, so 10. Okay, right subtree is 14, 13, fine. Okay, 14, left subtree 13. Okay, so this is also a binary search tree because all the nodes follow those two properties of the binary search tree. Okay. So binary search tree is basically a binary tree and therefore it can be traversed in order, pre-order and post-order. Okay, like a normal binary tree, you can also traverse the binary search tree in order, pre-order and post-order because a binary search tree is a special type of binary tree. Okay. So if we traverse a binary search tree in order and print the keys contained in the nodes of the tree, we get a sorted list of identifiers in ascending order. So this is the important property of the binary search tree. That is, if you traverse the binary search tree in order, you get a sorted list in ascending order. Okay, for example, traverse this binary search tree in order. Okay, so in order means left node right, L and R. Okay, so left subtree is traversed first. Okay, so leftmost node will be traversed first, which is 25, and you can see that 25 is the smallest value. Okay, then the root 30, then the right subtree of 30 contains two nodes 40 and 35. Okay, so 35, the left one will be traversed, then root 40. Okay, so this is the traversal of left subtree of the root, then the root LNR, so root 50, then the right subtree of root node. Okay, so here the left subtree of node 60 is empty. Okay, so you will traverse 60. Okay, then right subtree of the 60, this portion. Okay, so here 65 will be traversed, then the root of this subtree 70. This is the in order traversal of this binary search tree, and you can see this is sorted list in ascending order. 25, 30, 35, 40, 50, 60, 65, 70. Right? So this is the important property of the binary search tree. That is, if you traverse a binary search tree in order, you will always get a sorted list in ascending order. Right? So this is one of the important property of binary search tree. Obviously, this will be used in the searching process. Now, why binary search tree? Okay, because of this property. And how? So let us consider a problem of searching a list. Okay, so you are given a list and you have to search for a given item for a given value in the list, whether that item is present or not. If item is present, then what is its location? Okay, we have already considered this problem and we have seen two solutions for this problem using linear array and using linked list. Okay, the third is using the binary search tree. Let's compare all these three: linear array, linear linked list, and the binary search tree. Okay, so if you use array, okay, then searching becomes faster if you use a sorted array. Okay, so in the sorted array, the order of complexity for searching is order of log n base 2, right? Okay, but the problem with the linear array is that if you need to make changes, that is, if you try to insert new values or try to delete old entries, then it becomes slower because the order of complexity for insertion and deletion operation in the sorted array is order of n. You have to move half of the array elements either up or down the list, right? So searching in the sorted array is efficient, order of log n base 2, but insertion and deletion is not efficient. It is of the linear order. Okay, so solution is you can use linked list because it permits insertion and deletion to be carried out by adjusting only few pointers. Constant amount of steps are required for insertion. Okay, but the problem with the linked list is that you cannot perform binary search algorithm, right? You cannot perform binary search algorithm. Okay, you notice that I am saying binary search algorithm, not binary search tree. Binary search tree is a different thing. Binary search tree is a kind of binary tree, and binary search algorithm is a different thing. Binary search algorithm is an algorithm which is applied on sorted arrays. So binary search algorithm cannot be applied on linked list. Okay, so okay, so binary trees provide an excellent solution to this problem. Okay, what is the problem? The problem is that linear array provides excellent searching complexity order of log n, but insertion and deletion is not efficient. We have linked list. Insertion and deletion is efficient in the linked list, but searching is not efficient because you cannot perform binary search algorithm on linked list. Okay. So in the binary search tree, we have the order of complexity, order of log n for all the three operations, that is searching, insertion and deletion. For all these three operations, the order of complexity remains same, order of log n. Okay. So this is the advantage of binary search tree over the linear array and the linear linked list for searching. Okay, this from this table it will be more clear. Okay. Uh, Binary search tree, BST, linked list, and you can also use array. The array might be sorted or unsorted. Okay, so searching, insertion, and remove. Remove means delete. Right. So for these three operations, you can write the order of complexities for sorted, unsorted arrays, linked list, the binary search tree. First, consider the unsorted array. For the unsorted array, search complexity is order of n because the array is unsorted. Insertion order of 1 because the element will be added at the end of the array. Okay. Removal delete operation will require order of n because you must move the elements down the array to fill the vacant space. Right. Now consider sorted array. Okay, in the sorted array you can apply binary search algorithm. So search complexity is order of log n base 2. Insertion is order of n because the you must find the proper position of the new element in the sorted array. Okay, so order of complexity of this operation for the insertion operation is order of n. Removal again requires order of n operation because you must move almost half of the array on average to fill the vacant space. Linked list, okay. Searching complexity is order of n because you cannot apply binary search algorithm. Okay, insertion is simple order of 1. Okay, you can insert the new element either at the end or in the beginning. Removal is again complex order of n because you must first find the position or pointer of the node which is to be deleted. So you must traverse almost half of the linked list. Okay. Now binary search tree. In the binary search tree, the search complexity is order of log n, insertion complexity is also order of log n, and deletion complexity is also order of log. Okay. So you can see that the the BST has an edge over sorted, unsorted arrays and the linked list. Right. So BST has advantage over arrays and the linked list. Okay, what operations can be performed on binary search tree? Search, okay, search KT, search for key K in the tree T. If K is found in some node of the tree, then return true, otherwise return false. Okay, you can also return the pointer to the node containing the search value key K, right? Insert KT, insert a new node with value K in the info field of the node in the tree T such that the property of BST is maintained. Okay, that those two properties. The left subtree values in the left subtree must be smaller and the values in the right subtree must be greater. Right. Delete KT. Delete a node with value K in the info field from the tree T such that the property of BST is maintained. Okay. Find min and find max. Find the minimum and the maximum element from the given non-empty BST. So these four operations can be performed in the binary search tree. Okay, now how searching is performed in the binary search tree? Okay, it's very easy. You start with the root node. Okay, so you compare the target value, the item which is to be searched, with the element in the root node. That is, element means with the value stored in the root node. If the target value is equal, then search is successful. If target value is less, it means that that value might be in the left subtree of the root node. Okay, so in this case, you will search the left subtree. Okay, and if the target value is greater than the value stored in the root node, you will search the right subtree. Okay, and if the subtree, if any one, that is, if the left or the right subtree both are empty, it means that the search is unsuccessful. Okay. So search the left subtree. So again, this is the recursive definition. Okay, you will recursively search down the entire binary tree. Okay, example. So this is a binary tree and also a binary search tree because those two properties are fulfilled. Okay, so this is a binary search tree. Now try to search for 18. Okay, 18 is present here. Okay, so what is the process to search for a given number? So you start with the root node. Here root node is 30 and you are searching for 18. Okay, so now you compare 18 with 38. Since 18 is less than 38, so you will go to the left subtree. Okay, and the same process will be repeated. Now you will start, now you will compare 18 with the root of this left subtree. The root is 14. So 18 will be compared with 14. Now 18 is greater than 14, so you will go to the right subtree of the 14. This one. Okay. So also draw the path. So from 38 we reach to the 40, then from 14 we go to 30, 23, sorry 23. Okay, now 18 is compared with 23, so 18 is smaller than 23. Now you will go to the left subtree of the 23, this portion. Okay, now you will compare 18 with the root of this subtree. Okay, and the root is the node 18, so 18 is equal to 18, so search is successful. Okay, so this is the path traversed during the search process. Okay, now search for 75. Start with the root node. 75 is greater than 38, so you will go to the right subtree of 38. Okay, now 75 will be compared with the root of this subtree, 56. 75 is greater than 56, so you will go to the right subtree of 56. Okay, root of this subtree is 82. Now 75 will be compared with 82. Okay, so 75 is less than 82, so you will go to the left subtree of 82. Okay, the root of this subtree is 70. Now 75 will be compared with 75 will be compared with 70. Okay, so it is greater than 70, so you will go to the right subtree of 70, and the right subtree is empty. Okay, so whenever you find an empty subtree left or right, your search will stop and you will print that your search is unsuccessful. Okay, so this is the algorithm, the outline for searching in the binary search tree. This is the algorithm. Okay, and the algorithm is very simple. Okay, so these are some conditions. Okay, so algorithm name is find. Okay, so we have info left and right pointer. Okay, the node structure, the root variable, root pointer which points to the root node of the binary search tree, the item which is to be searched, and two pointers lock and parent. Lock points to the node containing item, and parent points to the parent of the node containing the item. Okay, so we consider the three scenarios. Okay, if lock is equal to null and parent is also equal to null, it indicates that the binary search tree is empty. If lock is not equal to null and parent is equal to null, it means that item is the root of the binary search tree T. Okay, because if the item is in the root node, then parent will be null because there is no parent for the root node. Okay, and if lock is equal to null and parent is not equal to null, it indicates that item is not in the binary search tree and it can be added as a child of the node n with location path. Okay, in fact this scenario will be used if we in this scenario will be used for the insertion algorithm. Okay, but here we are considering only the search algorithm. The name of this algorithm is find or search. Now the first step is, if root is equal to null, it means the binary search tree is empty, so simply set lock is equal to null and parent is equal to null and then return. Okay, step 2, if item is present at the root, so if item is equal to info root, then set lock is equal to root, parent null and then return. There is no parent for the root. Third step, okay, initialize ptr and save. ptr and save. If item is less than info root, then set ptr is equal to left root, because in this scenario you will traverse the left subtree if item is less than info root, and save is equal to root. Okay, this save pointer is for getting the parent pointer, right? Else, that is else item is greater than info root, then you must follow the right subtree, you must go to the right subtree. So ptr is set to the right root and save the parent, save is equal to root. Then the same process will be repeated for all the nodes along the path. Okay, so repeat step 5 and 6 while ptr is not equal to null, right? So until the you until you reach an empty left or right subtree. So if you find an item, item is equal to info ptr, then set log sol to ptr and save the parent value, par is equal to save and then return. Okay. And if item is less than info ptr, then again you follow the same process. Okay, that is save the parent pointer and go to the left subtree, ptr is equal to left ptr. Okay, else if item is greater than info ptr, then save the current parent and then go to the right subtree. Okay, so these two steps 5 and 6 will be repeated until you reach either a left or right empty subtree or item is found in the step 5. Okay, so if item is found in the step 5, then you will return, otherwise your search is unsuccessful and the lock is set to null and parent is set to save. Okay, that is the item is not present now, but it can be inserted as a child of the parent par, right? And then in the step 8 you exit. So this is the algorithm for searching in binary search tree. Okay, so this is the code snippet in the C language. Okay, it's very simple. This is the recursive code. Okay, okay, then insertion algorithm. Insertion, we will discuss this algorithm in the next lecture.